I want to start by defining a stochastic process. So a stochastic process is simply a sequence of random variables. So a stochastic process is a sequence x1, x2, so on, and it's an infinite sequence of random variables. Now, sometimes people prefer to have an uncountable set of random variables. We don't really need that in this course. So for now, you can just say that it's a sequence and it's a countable sequence. So I can just give them indices. And as usual, I forgot to start with 0. So let's start with 0, x0, x1, x2, so on. Okay. But we're interested in a particular type of stochastic process. And this is what we call a Markov chain or a Markov process. Actually, I really prefer the word Markov chain because there is something else in the literature called Markov decision process, which is a completely different thing. So let's just stick with Markov chain. So a stochastic process is a Markov chain if the expected value of every one of these variables is only dependent on the previous variable. And also not only the expected value, because sometimes these variables are not real. So imagine these are just variables that are mapping from my sample space to some other set, okay? So I want to say something like this. I want to say let Q be a set. I'm going to make it finite just to keep the definition easier. And suppose that Q is the range of all of these xi's, okay? So, and for every I, the range of xi, well, not exactly Q, but a subset of Q, okay? So basically, each one of my random variables is just going to choose one of the elements in Q. We say that this stochastic process is a Markov chain. We say x0, x1, so on. Is a Markov chain if it basically has no memory. And what I mean by no memory is that if I give you xn, you know the exact distribution of xn plus 1. Okay, so I want to say this. I want to say for every n and for every q, q was a value that can be taken by my random variables. Oh, by the way, this is not the set of rational numbers. This is just a finite set q. Okay, so I want to say this. I want to say the probability that xn is q, okay, if I have seen xn minus 1, if xn minus 1 was some other number, let's call it qn minus 1, okay, I want this probability to be the same no matter what came before xn minus 1, okay? So I want this to be the same as the probability of xn equal to q, given that x0 is q0, x1 is q1, so on, and xn minus 1 is q1. Okay, I guess now I have to change my quantifiers a little bit as well. So for every n, for every q, and for every q0 to qn minus 1. Okay. Okay, what am I saying here? I want you to think of this as a process that is going on in time. So let's say at any given time, I'm randomly choosing a member of Q, right? So x0 is what I chose at time 0, x1 is what I chose at time 1, and so on. And what I'm saying here is that what I choose at time n is only dependent on what I had at time n minus 1. It doesn't matter what the history was. Okay. Now, several things. First of all, This is conditional probability, but you probably haven't seen me write conditional probability like this. So when I write something like this, xn minus 1 is qn minus 1, this is actually an event, right? Because what is this xn minus 1? It's a random variable. So when I'm writing a condition like this, it means all the points, the set of all points in the sample space, such that if I apply this random variable to that point, it gives me this value. Okay, so this is an event, and this is also an event. So I can talk about the conditional probability. But of course, I can talk about the conditional probability only if the probability of the second event is not 0. Because remember, the probability of A given B was the probability of A intersect B divided by the probability of B. I cannot divide by 0. So here I have to add another condition that when these things exist, they're equal. So whenever the probability of these conditions is not 0, whenever I have these probabilities, they're equal. Okay. Now, this is the ugly definition that you will find people in statistics use, but we are computer scientists, so we have better definitions than this. I can define the same thing quite differently. And here's how I would define it. I would say a Markov chain, let's call it C, is a graph G and a function that assigns probabilities to edges of this graph. So let's call that P. Okay. Actually, I'm thinking, do I want to use P for paths later on? Probably, but I'm using it for probability anyway. Okay. So I have this where G is a directed graph. And so let me actually say that I have vertex set V, edge set E. And this P is a function that maps each of my edges to a probability 0. Okay. Now, I want to say that for every vertex, the sum of the probabilities of edges coming out of it is exactly 1. Okay. Such that for every vertex U, the sum over every V of P of UV is 1. Okay, so let's do an example. Let's say I have these states. So I have 1, 2, I have, let's say 3, 6. And let's say I have these edges. Now I want to also assign a probability to every edge. And the sum of the probabilities of the edges going out of every vertex should be 1. So this is my function P that is assigning a probability, and I'm going to write it in red. So let's say if I'm at 6, with probability half, I would go to 5, and with probability half, I would go to 4. If I'm at 5, there is only one outgoing edge, so it has to have a probability of 1. If I'm at 4, again, there's only one outgoing edge. I don't like that. Let's have 2. So let's say this one has probability 0.3, this one has probability 0.7. If I'm at 2, let's say this one has probability 0.1. Oh, there's again only one going. We have this one as well. And then this one has probability 0.9. If I'm at 1, let's say this one has probability 0.2 and this one has probability 0.8. And if I'm at 3, let's say this one has 0.01 and this one is 0.8. Okay. Now you can imagine what I want to do. I want to start at some particular point, and I want to take a random walk. And I'm going to walk forever. Right? And whenever I am at a vertex, I'm just going to say take the outgoing edge with the probabilities assigned to these edges. Okay, so whenever I'm at vertex 2 with probability 0.9, I will take this edge. With probability 0.1, I will take this edge. Okay, how does this fit into our previous definition of a Markov chain? So what is my set Q? My set Q is just my set of vertices V, right? And then Xi is just telling me where I am at time I. Okay, but I need one more thing to technically have the same definitions, to have the definitions be equivalent, and that's I need to know where I start. I need to have a starting vertex. So I can say that I also have some starting vertex V0. Okay. Now, to be honest with you, sometimes when I say a Markov chain, I mean a Markov chain with the starting vertex. Sometimes I just mean the graph and the probabilities. So I'm going to use the term for both of those things. And also generally, instead of having one starting vertex V0, I can just have a probability distribution over starting vertices. So I can say I start at this vertex with probability 0.1, I start at that vertex with probability 0.9 or something like that. Okay, that's also allowed. But it makes things unnecessarily complicated. So I'm just going to talk about the case where we have one starting vertex because everything else is just a trivial extension. Okay, so now I'm going to say that my xi is a random variable, and that's the vertex I am at time I. Okay. And of course, in this case, my x0 would always be v0. But then after that, everything is really random. Everything is just based on the probabilities that I have here. And why do I satisfy this rule? Because look, I'm just completely ignoring my history anyway. I'm saying whenever I am at a particular vertex, let's call that Qn minus 1, I'm going to take the edges that go out of it with the probabilities written on those edges. This is completely independent of my history. It's completely independent of how I got here. So of course it satisfies this. And you can see that the opposite side holds as well. Like if you are given a Markov chain, you can just create it, create its graph. Like, okay, great. But now we want to solve some problems about these Markov chains. But before I do that, I defined my graph. I told you that I have a starting vertex. Let's say I'm starting from vertex 1 here. And I talked about these random variables. I told you that the random variable xi is the vertex where I am at time I. But I didn't quite define my probability space, right? So what was a random variable? Remember, the definition of a random variable is that it's a function that maps from my sample space to some values. In this case, to the vertices of this graph, to the set V, right? But what is my sample space? So if I'm choosing something randomly, what is the thing that I'm choosing randomly? What is a sample here? Yes. So my sample space is the set of all infinite walks on this graph, right? So I have my, so this is what we have. We have the probability space. Let's call it S, and then I have a set F of events, and then I have a probability function P, right? And my set S is going to be the set of all infinite walks. So S is the set of infinite walks on my graph G. Well, I can say it's the set of infinite walks starting at the vertex V0, right? Or I can say I just take the set of all infinite walks, and if it doesn't start at zero, at V0, let's say its probability is 0, right? But I say the set of infinite walks on G starting at V0. Okay. But if I do this, then it means that V0 is a really important part of my Markov chain. So whenever I'm changing my V0, I'm technically changing my Markov chain. But that's not how I think about it, because I always think of the graph when I'm thinking of a Markov chain. So technically, I have several different probability spaces, one for every starting vertex. Okay, what is my set F? What are my events? So you see, I have an infinite set here, the set of infinite walks on G. Is this set countable? No. So just consider a graph that has two vertices, 0 and 1. And I have paths that can go from 0 to 1 or can stay in the same place. So consider this graph. I have 0 and I have 1, and I have all the possible edges. Right? The set of infinite walks on this graph is the set of infinite sequences of 0 and 1, which we've seen is not countable. Okay. So in general, my sample space is not going to be countable. So now, based on this, I want to define what's an event. Okay. So here's what I would do. Let's say I have a finite path instead of an infinite path. Can I intuitively assign a probability to a finite path? Yes, because look, if I, for example, want to look at the path 1, 2, 4, what is the probability that I take 1, 2, 4? It's just the product of the probabilities on the edges. So 0.2 times 0.2. Right. But the problem is that I'm working with infinite walks. I'm not working with finite walks. So what I can say is this. I can say, take a particular finite walk. For example, again, the walk 1, 2, 4. The probability that I take this is 0.2 times 0.1. So I have the probability of this finite walk. But I can also think of this as the probability of the set of all infinite walks that start with this finite walk. Right? So intuitively, I'm first taking this finite walk, and I know that its probability is 0.02. And then after that, I can extend my walk in any way. But if I consider the set of all infinite walks that can be obtained like this, their probability should be 0.02. Okay. So here's what I'm going to do. I'm going to say let W. So I'm going to write both vertices and edges. V0, E0, V1, E1, so on to Vn, be a walk in G. And this is, of course, a finite walk. Okay. I'm going to define the set of all infinite walks that extend W. Let's call that the extension of W. So I say the extension of W is just the set of all infinite walks. I don't know what to call them. Let's call them W bar since they're infinite. So they're in V omega. This is how we write like the set of infinite sequences on V, such that W bar is an infinite walk in G. And W is a prefix of W bar. But I'm assuming that there are no multiple edges. So if I have the set of vertices, the sequence of vertices, I also know what edges were taken. Okay, so basically, if the first n vertices in W bar is the same as the vertices in W. Okay, so now I can define my probability. I can say the probability of this set of the extensions of W is just the product of the probabilities of the edges in W. Okay, and this I goes from 0 to n minus 1. Okay, great. So remember, whenever I have a set S, I have to define, of course, also my events. Now I have defined some events and I have assigned some probabilities to them, but these are not all of my events, right? Because if I have two events, their union should also be an event. We had these rules that generally, if I have an event, its complement is an event. If I have a bunch of events, countably many events, their union is an event, and their intersection is also an event, right? But then I can just use the axioms to extend this. So I say my events are the extensions of finite paths, and anything that can be obtained as their unions or intersections, again, these are countable union and intersection, or complements, right? So whatever you can get from this, you can assign a probability to it. Now, a very tedious exercise would be to prove that this actually defines a unique set of events and a unique probability function. It does, just believe me. You can go and prove it. It will take you maybe 1 hour of time. Life is too precious for that. It's just too easy. Okay. So now I have my probability space. Now that I have this, I can define my xi's exactly, right? So let W bar be a sample, which means that it's an infinite walk on my graph. How do I define xi of W bar? It's just going to be the vertex at index I of W bar, right? So my random variables are mapping what? They're mapping infinite sequences of vertices to one vertex. And the idea is that xi is mapping this infinite sequence of vertices to the vertex that I was seeing at time I, at index I. So now my random variables are well defined. My underlying probability space is well defined. Everything is fine. Okay. But why did I do all of this? Because I want to actually solve some interesting problems. And before I can solve interesting problems, of course, I needed to have a well-defined setting for what I'm working with. Okay. So here's the first problem. Suppose that I start at vertex 1 here, and I keep walking. I take an infinite path, and of course, according to this probability distribution. Okay. What is the probability that I end up at vertex 6? If I start at 1, what is the probability that I end up at 6? 0, because there is no path from 1 to 6. Right? So if I consider the set of all infinite paths that start at 1 and have 6 at some point, that set is empty. And so, of course, the probability assigned to the empty set is always 0. Okay. But now, suppose that I ask you something else. I ask you, if I start at 1, what is the probability that I end up at 4? What is the probability that my path sees 4 at least once? This is called the reachability probability. So what is the probability that I reach 4 if I start at 1? And now you see that suddenly things are much more complicated. Because there are many ways I can reach 4. Right? I can go from 1 to 3 and then to 4. I can go from 1 to 2 and then to 4. Do I have any other ways? Okay. 1, 2, 2, 1. Yeah, so I can go 1, 3 back to 1, then 2, then 4. I can go 1, 3 back to 1, again 1, 3, and so on, and then to 4, and so on. So I have to sum up all of these, and it's actually quite hard, even when you consider a simple graph like this, but I'm considering general graphs. Imagine if I had a complete graph on n vertices and n was large, right? you're not going to be able to solve this. And of course, you will also need inclusion exclusion, because if you look at these finite paths, some of them are prefixes of some of the other ones. So for example, if let's say I have a bunch of paths that start from 1 and C4 10 times. I don't want to add their probability 10 times. I want to add their probability only once, right? So I have a problem. Now, the first thing is I have to make this well defined. So when I'm saying if I start at 1, what is the probability that I reach 4? Again, remember that we assign probabilities to events. So I have to define what exactly this event is. Okay. So I'm going to define the reachability event. And instead of having just one vertex 4, let's say I have a set of target vertices, and I want to say what is the probability that I reach any of these target vertices. I'm just going to extend it a little bit. So I'm going to say let T be a subset of my vertices. I want to see what is the event containing all the paths that visit T, okay? So I'm going to show it like this. So diamond T means, well, the way we read this is eventually T. So the set of paths that eventually at some point reach T, okay? And sometimes when people can't type diamonds, they just use F. But anyway, diamond T is going to be this. This is the set of all infinite walks such that there exists some index I such that my walk at index I is in T. So I have this set. Of course, it's a subset of my sample space because it's a set of infinite walks, right? But why is this set an event? Why is it measurable? It's because remember, I defined my events like this. I said extensions of finite walks are events, and then anything that you can obtain by union, intersection, or complement of these extensions is also an event. So the first thing I have to do before I ask what is the probability of diamond T is to prove that diamond T actually has a probability, right? So why is this an event? Yes. So basically I can do this. I can say let A be the set of all box W such that W is a finite walk on my graph, right? And let's say that I want this finite walk to end at T. And the last vertex of W, the last vertex of W is in T, okay? So I have a target set. I'm saying, look at all the finite walks that end at this target set, okay? Now, for each one of these finite walks, its infinite extension is an event. And this set is also countable, right? This is, again, something that we proved in set theory, because basically every vertex of W is coming from a finite set. So I have a set of finite sequences from a finite set. That set is either finite or countable, okay? So I can say that for every W in A, the set extension of W is an event, and A is finite or countable. So the union of these extensions, did I write extension with capital E before? Yes. Okay, so extension with capital E. So the union of all W's in A of extension of W is an event. Okay. But this is exactly the set that I was looking for. This union is exactly the set of infinite walks that visit T at some point, right? Because imagine I have an infinite walk that visits T at time I. I just take the prefix up to time I. That's a finite walk that ends at one of the vertices in T. And then if I extend it, I have my infinite walk in that extension, right? So this thing is exactly the set of all infinite paths that reach T. So great. All I did so far was to say that there is a well-defined probability. So if I ask you what is the probability of reaching a target set T, that's not a nonsensical question. It always makes sense. There's always a probability. Okay. How do I actually calculate it? So one thing I can do is I can take all the paths that reach T. So again, in this case, let's say my T is just my vertex 4. And I can take all these infinite walks that reach T and I can divide them into several sets. I can say, let's first look at the walks that reach T in exactly one step. Then let's look at the walks that reach T in exactly 2 steps, 3 steps, so on. And let's find the probability of each of these sets and let's just sum up the probability. Right? But my problem is that I might have some walks that visit T more than once. So I don't know, maybe I have a walk that comes to T after 100 steps, but then goes somewhere else, comes back to T again after 200 steps, right? So if I want to do something like this, it's really awful because I will have to do an infinite inclusion exclusion. And I don't want to do that, right? I want to do a much simpler thing. So I'm going to actually find a recurrence formula for this. So here's what I'm going to do. I'm going to define, again, I'm running out of things, so I'm going to just call it alpha. So I'm going to say alpha of V and T is going to be the probability that I reach T if I start my walk at V. Okay. Now, again, I told you that changing the starting position actually changes my Markov chain. So these are probabilities in different probability spaces, right? Because my probability space was dependent on my starting vertex. But anyway, this is well defined because I know that no matter what my starting vertex is, the probability that I reach a set of target vertices is an event. Okay. So let's say alpha of Vt is the probability that I reach T if I start my walk at vertex V. Okay. Can I find a recurrence relation for this alpha of Vt? Okay. Let's do something like this. First of all, let's do a case fork. Let's say V itself is a target vertex. If this happens, what is alpha of Vt? It's 1, right? Because I'm starting at vertex V and I want to reach one of the target vertices, but V itself is a target vertex. So if I start at a target vertex, I'm definitely seeing a target vertex at the very beginning. So the probability is 1. Okay. So the other case is if V is not in T. Now let's look at my graph. I have my vertex V and it has a bunch of edges going out to other vertices. So let's call those vertices U1, U2, so on to UK. Okay. And each of these edges has a probability assigned to it. So let's say this is P1, P2, PK. Or actually, I can just write P of VU1, right? Instead of doing that. So the probability of this one is P of VU1. The probability of this one is P of VU2, and so on. And this is P of VUK. So if I start at vertex V, I know what's the probability of taking each of these edges, right? And after I take an edge, I know what is the probability to reach my target if I start at U1. That's just alpha of U1t, right? So what I have in this case is a very simple recurrence. I can say alpha of Vt, capital T, is going to be alpha of U1t times this probability. Or actually, let me just write it as a sum directly. So this is going to be the sum of I from 1 to k, the probability of taking this edge, probability of VUI, times the probability of going from the vertex UI to my targets. Okay. So I definitely have this equality. Great. Now, does this always give me an answer? So let's do something very simple. Let's say I have these vertices, 1, 2, and 3. Okay. And let's say I have these probabilities. So if I'm at 1, let's say with probability 0.2, I stay at 1. And with probability 0.2, I go to 3. And with probability 0.6, I go to 2. Okay. If I'm at 2, let's say with probability 0.5, I go to 3. And with probability 0.5, I go back to 1. And if I'm at 3, let's say with probability 1, I just go to. So let's say this is my Markov chain. And let's say my starting vertex V0 is just 1. And let's say my target is only the vertex 3. So I want to see what is the probability that I reach this vertex. Okay. Now I'm not going to write alpha of Vt anymore. I'm just going to write alpha with the subscript telling me that the vertex that I'm starting at. So what is alpha 3? Alpha 3 is 1. Because if I'm at 1, if I'm at 3 with probability 1, I have seen my target set. Okay. What is alpha 1? Alpha 1 is going to be 0.2 times alpha 1 plus 0.2 times alpha 3 plus 0.6 times alpha 2. Okay. And what is alpha 2? This is 0.5 times alpha 1 plus 0.5 times alpha 3. Now, as you see here, this is not exactly a recurrence relation, right? Because alpha 1 depends on alpha 2, and alpha 2 depends on alpha 1. I mean, hell, even alpha 1 depends on itself here, right? So I have a problem, and the problem is that generally, whenever I have a cycle in my graph, I will have a cycle in the dependencies between my alpha variables. Right? But does that really matter? No, because these are linear equations that are solved linear equations. Right? So I have n variables, in this case 3 variables, and I have 3 equations. I can solve it. Right? Now, in this case, if I solve it, the answer would just be 1. Like alpha 1, alpha 2, and alpha 3 will all be 1. Right?
like there always be a solution.
Okay. Why is there always a solution, and why is there always a unique solution? That's a really good question. So here's one thing I'm going to do here. I'm going to add another vertex. Let's say I have this vertex 4, and I'm going to have just a self loop with probability 1. Okay. So what happens here? I will have that alpha 4 is equal to alpha 4. Right. So I can assign whatever probability I want here. So it's definitely not the case that this system of equations has a unique solution. I'm giving you a system of equations that has infinitely many solutions. You can apply whatever you think you want to alpha 4. Basically, you can give it any value between 0 and 1. Oh, I have to also add those conditions as well, right? So all of my alpha i's are between 0 and 1. Okay. So it's possible that this system of equations has infinitely many solutions. Is it possible that it has no solutions at all? No. Why? Because these probabilities exist, right? We have already proven that these probabilities exist. So this set, the set of all paths that reach the target, is a measurable set. It's an event, no matter where my starting point is. Okay, so these probabilities exist. And of course, if these probabilities exist, then they satisfy these equations. So the equations have at least one solution, which is the correct probabilities that we're looking for. But the problem is that we might have several solutions. Okay. So here's the thing. Before writing these equations, what I can do is just give you a simple graph reachability and just say that if I have a vertex that doesn't have any path to my target vertices, then set the alpha value for that vertex to 0. Right? For example, in this case, 4 just doesn't have any path to the target vertex 3. So of course, if I start at 4, the probability that I would ever reach 3 is just going to be 0. Right? So I can find this by a DFS. I can just do a reverse DFS from 3, see what is the set of all the vertices that have paths to 3. And then for every vertex that doesn't have a path to 3, I would just add another case. So case 0, if V has no path to T, then just set this alpha of VT to be 0. Okay. Is this enough to make sure I have a unique solution? So with this new rule, it means that when I have a situation like this, when I have a vertex like vertex 4 here that cannot reach any of my target vertices, I'm not going to add an equation that just says alpha 4 is equal to alpha 4. Instead, I'm just going to add an equation saying that alpha 4 is 0. Okay. So this is good because it helps me with some of my problems. At least now I cannot have many different solutions due to having different values for alpha 4. I know that my alpha 4 has to be 0. But can I claim that the rest of the system, or like the whole system now after I've set alpha 4 to 0, actually has a unique solution? And look, if I can prove that my system has a unique solution, that's all I wanted, because I know that whatever my reachability probabilities are, whatever the probabilities of these sets, these events of reaching T is, they're going to satisfy these equations. And if these equations have only one solution, then of course that solution is going to be the probabilities I'm looking for. Okay, so I want to show that my equations have exactly one solution. Now, if you've passed linear algebra, the standard way of doing this is that you prove that you have n equations and these n equations are linearly independent.
And then that would prove that they have a unique solution. But we can do this kind of combinatorially here. So let me show you a simpler proof that there is only one solution to this system of equations. What I want to do here is I want to remove some variables. So let's say, for example, if I want to remove alpha 2 from my system, what can I do? I can say, well, alpha 2 is equal to this. So I can remove alpha 2 from the system, and whenever I see alpha 2, I can just substitute it with this expression, right? And then I will have a system on n-1 variables. Now, if my system on those n-1 variables has a unique solution, then when I add alpha 2 back, alpha 2 is this particular linear combination of my other n-1 variables. So that means my system on n variables is also going to have a unique solution. Okay, so the question is, can I remove my variables one by one? Now, again, you can look at this and you can try to argue based on the system that you can remove the variables, but I want to argue based on the graph. Basically, what does removing variables look like in the graph? Let's say I have a particular vertex V, okay? And let's say it has a bunch of predecessors. So U1, U2, blah, blah. And it has a bunch of successors. Let's say U prime 1, U prime 2, yeah, so on. Now, there are edges from predecessors to V and from V to its successors, of course. And I'm defining one variable alpha of V here, right? And each of these edges has some probability assigned to it. So it has, this one has probability of U1V, this one has probability of U2V, this one has probability of VU prime 1, probability of VU prime 2, and so on. Okay. So when I'm removing V, what am I doing? I'm saying that I have this alpha V and I have an equation for it, which is basically this probability times alpha of U prime 1, this probability times alpha of U prime 2, and so on. By the way, sorry for the coughing, I'm very badly cold. Now I'm going to take that equation and I'm going to use it to rewrite alpha V in my system. But where does alpha V appear? Alpha V appears in the equations for these previous predecessor vertices, basically. Okay. So what does removing alpha V look like in my graph? And this is basically the same as saying I'm removing the variable V, right? So I'm removing the vertex V. So I'm going to have U1, U2, and all of the other predecessors. I'm going to have all of the successors, U prime 1, U prime 2, all the way. And then I'm removing this vertex because I'm removing its corresponding alpha from the system. But I'm replacing that alpha with this expression, right? And because I'm doing that, it's basically the same as saying I'm now adding an edge from U1 to U prime 1, an edge from U1 to U prime 2. Basically, I'm going to add an edge from every predecessor to every successor. So it's like creating this new Markov chain in which that vertex V is removed, but now every predecessor has an edge to every successor. Now, what is the probability that I should write for this edge? You can find this probability by going over the system, or you can just use your intuition based on the graph. So if I start at U1, what is the probability that I go to U prime 1? Well, it's just going to be the product of the probability of this edge and the probability of this edge. So P of U1V times P of V U prime. And similarly, the probability of this edge is going to be the probability of this edge times the probability of this edge, and so on for every one of these edges. Now, of course, if one of these edges existed before, so if even before removing V, there was an edge from U1 to U prime 1, this will be added to its probability. It's not just going to be the probability itself. Okay, but what does this mean? This means that I can look at all of the vertices that don't have just a fixed value assigned to them. So I have assigned 0 to some vertices and I have assigned 1 to some other vertices. I can look at every other vertex, every vertex that is in this case, and I can just remove it from my graph, right? So I'm removing this vertex V, but none of the reachability probabilities, none of the alphas for the other vertices are really changing, which is again the same as saying that I'm removing alpha V from this system of linear equations. Okay, great. So now this whole thing is just a matter of induction. And I'm doing induction on the number of vertices that are in this case. So if I have 0 vertices in this case, it means that for every vertex, I know that the probability is either 0 or 1, so I have a unique solution. Now, if for the case where I had n minus 1 vertices, I can assume as my induction hypothesis that the system has a unique solution, then when I have n vertices, I just take this vertex V, remove it. Then now I have n minus 1 vertices, it has a unique solution. So I have a unique solution here. When I put vertex V back, I know what alpha V is going to be. Alpha V is just P of V U prime 1 times alpha of U prime 1 plus P of V U prime 2 times alpha of U prime 2, so on. So when I add alpha V back, I'm going to have a unique value for alpha V as well. So this system is always going to give me a unique solution. Great, and this solution is of course going to be the probabilities that I'm looking for. Nice. So of course, you can solve this just by Gaussian elimination. So now we have an algorithm that given a Markov chain and a starting position, a starting vertex, and a set of target vertices tells us what is the probability of reaching those target vertices. Okay, nice. Now I want to define a different kind of event. And this other type of event is going to focus on the paths that see my target set not just once, not even a finite number of times, but an infinite number of times. So this is called a Buki set. Actually, it shouldn't be pronounced something like Bushi, but I mean, that's too hard to pronounce, so Buki. And this is what I'm going to say. I'm going to say that I have a target set T, subset of my set of vertices. And what I want to ask is, what is the probability that my infinite walk sees T infinitely many times, infinitely often? Okay. So I'm going to define that set. I'm actually going to show it like this. So this is the set. So the way we read this is globally eventually T, but forget about the notation, just focus on the fact that I want to find all the infinite paths that see vertices in T infinitely many times. So this is going to be the set of all W bars, where W bar is an infinite path on my graph G, of course, starting at V0. I don't write starting at V0 everywhere, but we are assuming that we're only considering paths that start at V0. Oh, sorry, infinite walk on G, starting at V0. And I want to also say that there are infinitely many places in W. So there exist indices I0 less than I1 less than I2, so on, an infinite number of indices, such that for every J, Wij is a vertex in T. Okay. So all I'm saying here, so this was W. All I'm saying here is I want to look at the set of all the infinite walks on G, starting at my vertex V0, that visit my target CT infinitely many times. So this W bar is visiting T at time I0, I1, I2, so on, and this is an infinite sequence. Okay. And of course, what I want to find is the probability of this set. And I can also just show this as the set Buki of T. Okay. And by the way, this is the name of a scientist. It's named after him because he was defining automata based on these kinds of properties, and he had a lot of really interesting results. Okay. Now, again, just like the case of reachability, I have to figure out whether this is even an event. Is Buki of T an event? Well, here's what I can do. I can say, again, let's look at finite paths. So let me say I define a set A1, and I say this A1 is the set of finite walks on my graph G that visit T exactly once. Okay, so these are the W's such that W is a finite walk on G that visits my target set exactly once. Well, I don't need to say exactly once. I can say at least once. Okay, so W is a finite walk on G, and there exists some index I1 such that WI1 is in T. Okay, so A1 is the set of all the finite walks that visit my target set T. Now I say A2 is the set of all finite walks that visit it at least twice. So I want to say there exist two indices, I1 and I2, such that WI1 and WI2 are both in T. Okay, so at two different times, I1 and I2, my walk was in my target set. And similarly, I can define the set AK as the set of all finite walks W such that W visits T at least K times. Okay. Great. Now, what happens if I look at the extensions of all the walks in A1? So this will give me all the infinite walks that are seeing my target set at least once. What if I look at the extensions of all the walks in A2? This would be all the infinite walks that see my target set at least twice, and so on. So I'm going to define these sets. I'm going to say B1 is the union of extensions of W where W is in A1, right? So I'm taking all the finite paths that were reaching my target set at least once. I'm saying, look at their extensions. I'm taking the union of all of these extensions. Okay, intuitively, again, B1 is the set of infinite walks that visit my target set T at least once. Okay, now I can do this with other sets A2, A3, so on as well. So I can say B2 is the union of all the W's that are in A2 of the extensions of W. And basically the idea here is that W itself is seeing my target set twice. So of course, every extension of it is seeing the target set at least twice as well. On the other hand, if I have an infinite walk that is seeing my target set twice, I can cut it after the second visit. And that's going to give me a finite prefix that visits my target set twice. So these are going to be the infinite walks that visit T at least twice. Okay. And generally, I can define BK to be the union of W in AK of the extension of W. Okay. So this would be the set of infinite walks that visit T at least K times. Nice. Now, I want you to realize that this A1 to AK, these are countable sets. So, and these are events. So B1 to BK, each of them is a countable union of events. So each of B1 to BK is an event. But now what happens if I look at the intersection of all the BIs? So let's say I have the intersection of I from 1 to infinity of BI. Okay. What kind of walks are going to be in this intersection? So if an infinite walk is in this intersection, it is in B1. So it visits T at least once. It's also in B2, so it visits T at least twice. It's in B3, so it visits T at least 3 times, and so on. So it has to visit T infinitely many times, because if it only visits T a finite number of times, let's say if it visits T n times, then it's not going to be in Bn plus 1. So if I have a path, if I have an infinite walk that is in the intersection of all the BIs, that's precisely saying that this infinite walk is seeing my target set T infinitely many times. So this intersection is exactly the set Buki T. Okay, but now this is a countable intersection of a bunch of events, so it's an event. So I did all of this to show that this set Buki T is an event, and so it means that it has a probability associated to it. Okay, great. Now we want to find the probabilities of these Buki sets. What is the probability that I see my target set T infinitely many times? But I'm especially interested in this when this T has only one vertex, because if I solve it for that case, you will see that I can actually solve it for the general case as well. Okay, so actually with a slight abuse of notation, I write Buki of V when V is a vertex, and what I mean here is Buki of the set containing V. Okay, so all the paths are all the infinite walks on my graph that visit the vertex V infinitely many times. That's Buki V. Now I'm also going to extend my notation a little bit, and I'm going to write things like BK of V. And what I mean is like this set BK when my target set was just the vertex V. Okay, so I want to refer to these sets when my target set is just one vertex V, and I just do that like this. I write BK of V, which is just this set BK when T has only one vertex in it, and that one vertex is V. Okay, so now I want to prove some interesting things. And interestingly, I'm going to look at conditional probabilities. So here's what I want to say. Suppose that I have some vertex U, and let's say that this vertex U has an edge to a different vertex V, and this edge has some probability. And by the way, I'm going to assume that the probabilities of all of my edges are positive, because if I have an edge with probability 0, I can just remove it from my Markov chain. And that doesn't change anything, right? So then it makes no sense to have edges of probability 0 in your Markov chain. So let's say I have this edge from U to V, and it has some probability. Let me call that probability Q. Okay. Here's what I'm interested in. I'm interested in the probability that I see V infinitely many times. So probability of the Buki of V conditioned on that I've seen U infinitely many times. So Buki of U. This is what I want to compute. Okay. So first of all, conditional probability only makes sense if this second part, the condition, has non-zero probability. So I'm just going to assume that. I'm going to say, suppose that the probability of Buki U So the probability that I see the vertex u infinitely many times is not 0. Then what is this probability? What is the probability that I see v infinitely many times? Okay. But before answering this, let me answer a simpler question. What is the probability that I even reach v conditioned on bookie u? So what is the probability that I reach my vertex v conditioned on knowing that I've seen the vertex u infinitely many times? Well, intuitively, this is quite easy to understand, right? So I'm taking some path, some infinite walk on my graph, and I'm coming to the vertex u infinitely many times. Every time I'm coming to u, there is a non-zero probability that I go to v. So it seems quite obvious that this probability should be 1, right? And to see this, let's just consider it like this. Let's say, what is the probability that I go to v immediately after the first time that I'm seeing u? Well, that's just q. So the probability that I don't see v immediately after the first time that I see u is just 1 minus q. Okay. Now let's extend this. Suppose that I have seen u twice. So I've come to this vertex u twice. What is the probability that I've never gone to v? Well, if I don't want to go to v, every time there's a probability of 1 minus q of not going to v. So the probability is going to be 1 minus q squared, right? And generally, if I come to u n times, the probability that I never go to v is going to be at most 1 minus q to the power of n. And I say at most this much because, well, maybe in my past I go from u to somewhere else and then from there to v, and I'm not even considering those. I'm just saying just the probability that I don't take this edge is 1 minus q to the power of n. So the probability that I don't see v is at most 1 minus q to the power of n, assuming that I have seen u n times. Okay. So what I just proved here is that the probability that I don't see v, so the set that sees v, but it's complement of the reachability set of v, given that I've seen u n times. So this was the set bn of u, right? This is going to be at most 1 minus q to the power of n. Okay. And of course, as n tends to infinity, you can see that this set tends to bookie of u, and this probability tends to 0. So it's very easy to now say that the probability of not reaching v, so the set of vertices that reach v, but its complement, given bookie of u, is 0, which immediately gives me this thing that I wanted. So the probability of actually reaching v, if I know that I'm seeing u infinitely many times, is 1. Okay. But this is not exactly what I wanted. So I'm just saying that if I know that my infinite path is coming to u over and over again, infinitely many times, the probability that it never takes this edge and never goes to v is 0. So with probability 1, it will eventually go to v. But I want something even better than this. I want to say that with probability 1, I'm going to see v infinitely many times. So I want to say that the probability of bookie of v conditioned on bookie of u is actually 1. Again, sorry for my coughing, I'm very badly cold. Okay. So here's the thing. I know that the probability of reaching v conditioned on bookie of u is 1. Okay. Now, what is the probability that I see V exactly once, conditioned on bookie of U? So again, I know that I'm seeing U infinitely many times. What is the probability that I see V only once? I claim that probability is 0. Because look, I'm coming to U infinitely many times, and then at some point I will go to V, right? But even after that point, I'm still coming back to U infinitely many times. So if I say that I will never go to V again, that's the same as this one. Sorry, it's the same as this one. Probability of never going to V given bookie of U, which I know is 0. So probability of going to V exactly once given bookie of U is also 0. Similarly, you can argue that if I'm seeing U infinitely many times, the probability that I see V only twice is 0. The probability that I see V only 3 times is 0. So generally, for every natural number n, the probability of seeing V exactly n times conditioned on the fact that I'm seeing U infinitely many times is going to be 0, right? Because I can make the same argument. I can say, well, after I see V n times, I'm still going to see U infinitely many times. So if I see V exactly n times, it means that after the last visit to V, I have infinitely many visits to U, but I'm never visiting V. So I'm in this case, which I've already shown is 0. Okay. But now look at these two things. I know that assuming that I'm visiting U infinitely many times, with probability 1, I will visit V. But for every n, the probability of seeing V exactly n times is 0. But here's the thing. I can say that the set of all paths that visit V, the set of all, again, infinite walks that visit V, can be divided into a bunch of sets. I can say this is going to be the union over every n of the set of walks that visit V n times. Okay, exactly n times, right? So these are going to cover all the walks that see V a finite number of times, but this is going to be unioned with bookie of V. All I'm saying here is that, well, this is the set of all walks that visit V. If a walk visits V, it either visits V once or twice or 3 times or n times, or it visits it infinitely many times. So I'm writing the finite cases here, I'm writing the infinite case here. Now, I've just shown that the probability of all of these things is 0. And I've shown that this one has a probability of 1. So this one must have a probability of 1 as well. Okay. And again, all of these are conditioned on bookie of U. So I just proved that this probability is 1. So this probability has to be 1. What does this mean? This means that if someone tells me, if I have the information that I'm going to see a vertex in my Markov chain infinitely many times, I also know that I'm going to see every one of its successors infinitely many times with probability 1. Okay, great. So now let's just look at what happens if my Markov chain, and again, when I say Markov chain, I mean the Markov chain where the probability of every edge is non-zero. I want to see what happens if my Markov chain is strongly connected. So I'm going to say, suppose the underlying graph G is strongly connected. So it just has one strongly connected component. There is a path from every vertex to every other vertex. Okay. So for example, I can go up here. Yeah, I can copy this one. This is strongly connected. And let's say I have a starting vertex, V0. Now, here's the thing. Consider my entire sample space S. I claim that S is bookie of 1 union with bookie of 2 union with bookie of 3. Or in general, I would say that S is the union over all vertices, every vertex V, of bookie V. Why is this the case? Well, that's quite easy to see, actually. I'm having an infinite walk on my graph. So whenever I have an infinite walk, since I have a finite number of vertices, by pigeonhole principle, there is a vertex that I'm seeing infinitely many times. So every infinite walk is going to be in the bookie set of some vertex. So my entire sample space is the union of bookie of V for all vertices V. Now, of course, these sets don't have to be pairwise disjoint because I can have a walk that visits 1 infinitely many times and also visits 2 infinitely many times. But S is the union of these sets. Okay. But what does that tell you? I know that S is the union of bookie of V, and I also know that the probability of S is 1. That's an axiom, right? So there should be some bookie V that has non-zero probability, because if all of them have probability 0, then their union should also have probability 0, which means S should have probability 0. That's not possible. So there is at least one vertex V such that bookie of V has non-zero probability. Okay, so I'm going to say let V be a vertex such that the probability of bookie of V is not 0. Okay. But what do I know? I know that if I have two vertices like this, if I have U and V, the probability of bookie of V given bookie of U is 1. So now if I take some other vertex that is a successor of V, so I'm going to say let V prime be a successor of V. Then I've already shown that the probability of bookie of V prime given bookie of V is 1. Okay. But what does this tell you? Just use the definition. This probability is the probability of the intersection of these two sets divided by the probability of the second one. So just to make it simpler, let me show it like this. Suppose that I have proven that the probability of A conditioned on B is 1. What does that mean? That means that probability of A intersection with B divided by probability of B is 1, right? So probability of A intersect B is the same as the probability of B, which means that probability of A, which has to be greater than or equal to this one, because A intersect B is a subset of A, is greater than or equal to the probability of B. Okay, so what I have here is that if I have a vertex V, and if I have another vertex V prime that is a successor of V, then the probability of bookie of V prime is greater than or equal to the probability of bookie of V. Okay, but here's the thing. I said consider the case where my graph is strongly connected, right? So from every vertex, I have a path to every other vertex. But whenever I have a path, as I'm going from, let's say, 1 to 2 and 2 to 3 and so on, the probability of the bookie set is increasing. So all of my vertices are going to have the same probability for their bookie sets, right? And what is that probability? That probability is actually 1. The probability of the bookie set for every vertex is going to be 1. Because think about it, if it's anything other than 1, basically what I'm saying, based on what I've had here as well, is that the probability that I see any vertex infinitely many times is less than 1. But that's impossible because I have to see at least one vertex infinitely many times. Okay, so what we proved here is that if my Markov chain G is strongly connected, if it has only one strongly connected component, then every vertex will be visited infinitely many times with probability 1. So if G is strongly connected, then I have that for every vertex V in V, the probability of the set bookie V, which is the set of all the walks that visit the vertex V infinitely many times, is 1. So basically with probability 1, I'm going to visit every one of my vertices infinitely many times. Does this mean that every infinite walk visits every one of my vertices infinitely many times? No, of course not. For example, here I have a walk that just stays at 1. Of course, it's not going to visit every one of my vertices infinitely many times. But what this says is that the probability of that is 0. Okay, so with probability 1, I'm going to visit every vertex infinitely many times. And also the intersection of these bookies has probability 1 as well. You can just prove it in the same way as. Okay, nice. So now what happens if my graph is not strongly connected? So suppose G is not strongly connected. Well, in this case, I can look at all the strongly connected components of G. So let's say I have a bunch of strongly connected components, right? And some of these strongly connected components are going to have edges to some of the other strongly connected components. So let's say there are edges from here to here, maybe several. Let's say I have this kind of edge, this kind of edge, have this, okay? So we've seen before in the graph theory module that if I take each one of my strongly connected components and I just collapse it into one vertex, if I merge all the vertices in the same strongly connected component, what I get is a DAG. So if I look at each of my strongly connected components as one vertex, this is now a directed acyclic graph. Okay. So I'm going to define the concept of a bottom strongly connected component. A bottom strongly connected component is a strongly connected component that doesn't have any outgoing edges. Okay, so this one is a bottom strongly connected component. This one is a bottom strongly connected component. But for example, this one isn't because it has an outgoing edge. Okay, so a BSCC or bottom strongly connected component is an SCC, a strongly connected component without any outgoing edges. Okay. So let's say I start my walk somewhere, and let's say after a while, I reach one of these bottom strongly connected components. So let's say after a while, I take this edge and I enter this bottom strongly connected component. Now I can never exit it because it's a bottom component. It doesn't have an edge to anywhere outside of it. So I would be back to this case. I would be back to the case where I have a strongly connected graph. It's just that my strongly connected graph is just this bottom strongly connected component. So this means that if I ever enter a bottom strongly connected component, I'm just going to go around this component forever. And based on what I proved here, I'm going to see every one of its vertices infinitely many times with probability 1. Okay, great. So I know what happens if my walk enters a bottom strongly connected component. But will I always enter a bottom strongly connected component? Well, the answer to that is also yes. Because suppose that I'm in a component that is not bottom. So let's say I'm here. I claim that with probability 1, I would actually exit this component. Why is that the case? So here's the thing. I can just look at my bookie sets again. I can say there are going to be some vertices that I'm going to see infinitely many times. Okay. Now suppose that the probability of exiting this strongly connected component is not 1. So with some non-zero probability, I'm going to stay here forever. But if I stay inside this strongly connected component forever, I know that I will see each one of its vertices with probability 1 infinitely often. Okay? So the probability of seeing each one of these vertices conditioned on not leaving this particular strongly connected component is 1. Okay? So this is what I'm saying. Let's give it a name. Let's call this strongly connected component C1. I'm saying what is, and let's say I have some vertex V in C1. What is the probability of bookie of V conditioned upon never leaving C1? Okay. Now, of course, what I want to prove is that the probability of never leaving C1 is 0, and so this probability doesn't even make sense. But let's say I use proof by contradiction. I say, suppose that I don't leave C1 with probability 1. So the probability of staying in C1 forever is non-zero. If that's the case, then I can talk about the probability of this event, seeing V infinitely many times, conditioned on never leaving C1. And since I'm never leaving C1, this is going to be 1 because, again, I can do the same argument that I made here for the strongly connected case. Okay. Great. So now let's consider one of the border vertices, because this holds for every vertex in C1, right? So let's just consider a vertex V that is here, that has an edge to another component. So if I never leave C1 with probability 1, I'm going to see V infinitely many times, right? But this means that, let's say its successor here is V prime. I've already proven that the probability of bookie of V prime given bookie of V is 1, right? So combining these two things together tells me that the probability of bookie of V prime given never leaving C1 is 1. Which is ridiculous, right? This is definitely a contradiction. Because if I'm never leaving C1, I'm never going to see V prime, let alone seeing it infinitely many times. But I'm saying the probability of that is 1. So this is definitely a contradiction. Of course, here, instead of bookie of V prime, I could just use reach of V prime. I could make the same argument like this. I didn't need to just use bookie. I could say this. I could say, if I have my V prime here, the probability of reaching V prime given bookie of V is 1. Again, we proved this before, right? So now the probability of this event given this one is 1, but the probability of this one given this one is also 1. So the probability of the first event given the last one, and never leaving C1, is also 1. Right? But again, this is a contradiction, because if I'm reaching V prime, I'm definitely leaving C1. Right? And this contradiction started from the assumption that the probability of never leaving C1 is non-zero. So the probability of never leaving C1 has to be 0. So with probability 1, I'm going to leave C1. Okay. And the same argument can be applied to any strongly connected component that has an outgoing edge. As long as your strongly connected component is not a bottom strongly connected component, you're going to leave it with probability 1. Okay. So what did we find out so far? I'm saying no matter where I start my walk, so let's say I start my walk somewhere here, let's say this is my V0. With probability 1, I'm going to leave my current strongly connected component if it's not a bottom component. And if I go to another non-bottom component, again, with probability 1, I'm going to leave it. So with probability 1, I'm going to end up in a bottom strongly connected component. And when I end up in a bottom strongly connected component, I'm going to see all of the vertices in that bottom strongly connected component infinitely many times, again with probability 1. So if I ask you, when I start at V0, what is the probability that I see a particular vertex U infinitely many times? You say, well, if U is not in a bottom strongly connected component, then that probability is 0. Because with probability 1, I'm leaving the component of U, which means that I'm not going to come back and I'm never going to see U again. So U is seen only finitely many times. But if U is somewhere here, if U is in a bottom strongly connected component, I ask you, if I start at V0, what is the probability that I see U infinitely many times? Well, first you have to figure out what is the probability that I end up in this bottom strongly connected component? Because it might be possible that there are several different bottom strongly connected components that I can go to. Okay, so what is the probability of reaching this bottom strongly connected component? But we've seen how to compute that. I just say this is my target set T. What is the probability of reaching T? Okay. So I find the probability that starting at V0, I would end up at this bottom strongly connected component. But I know that if I end up at this bottom strongly connected component, then with probability 1, I'm going to see U infinitely many times. So the probability of seeing U infinitely many times is the same as the probability of reaching this bottom strongly connected component. Great. Now, this means that for every vertex U, I just told you how to compute Buki of U's probability. So the probability of Buki of U is going to be 0 if U is not in a bottom strongly connected component. And it's going to be the same as the probability of reaching the bottom strongly connected components. Let's actually call it T. If U is in T and T is a bottom strongly connected component. Okay. But how do you extend this if I have more than one vertex? So let's say I've given you several vertices and I've asked you what is the probability that I see them infinitely many times. So the general case of Buki. Well, I just have to look at my bottom strongly connected components. If I have a bottom strongly connected component that doesn't have a target vertex, that doesn't contribute anything. So what I'm asking you is, what is the probability that I reach one of the bottom strongly connected components that has a target set in it? And you just sum up the reachability probabilities. So just go over every bottom strongly connected component that has a target vertex in it and ask what is the probability of reaching. Okay, that's it for this session. I'll see you next week.